Today's
Yeah, I think so.
seminar. I welcome everyone and also welcome Professor Asmita Mukherjee, who readily agreed to give today's faculty seminar. So she did her PhD from Saha Institute of Nuclear Physics, and after that, what she did, she told me not to tell. she's been here for several years now. We all know her. So thank you very much, Professor Mukherjee, for agreeing to give the talk. So she will be talking about Nucleon Tomography in J over psi production at the future electron-ion corridor. Please go on.
Thanks, Shomo. Am I audible?
Yes, you are audible.
Okay, so great. So actually, I gave more or less the same talk at Brookhaven in July. Then I wanted to modify this talk a bit. Actually, I was supposed to talk next week, but because of a last-minute cancellation, Shomo asked me to give the talk today, and he called me on Monday. So I could not manage to do the modifications that I planned, and so some of the slides might be a little bit technical. But nevertheless, let us start it. So the topic that I'm going to talk about is Nucleon Tomography in Jepchi production at the future electron-ion collider. Now there are two words here. One is tomography, the other is Jepchi. So tomography is basically trying to understand the internal structure of a three-dimensional object by taking multiple two-dimensional slices. Okay. So here we are going to talk about nucleons, that is proton and neutron. And these are three-dimensional objects built from quarks, antiquarks, and gluons. So the idea is to study the internal structure of these tiny, tiny objects, the building blocks, using this tomography. How to do it, that is what we are going to discuss. And Jepchi is a particular particle that also I'll introduce. Okay, so the topic of this talk is to understand or try to understand the structure of the nucleons in terms of quarks and gluons. This topic has still not been understood clearly or completely. So you see, the matter, all the matter that we see around us is built up of atoms. So the size of the atoms are roughly 10 to the power minus 10 meters. So inside the atoms, there's this nucleus, and the electrons rotate in orbits around this nucleus. So the size of the nucleus is roughly 10 to the power minus 14 meters. These nucleus contain the nucleons, that is protons and neutrons bound together. So the size of the protons and neutrons are roughly about 10 to the power minus 15 meter. That is, if you go to at this distance scale, you will be seeing the nucleons, that is protons and neutrons. Again, these protons and neutrons are not the fundamental building blocks of matters. Inside these protons and neutrons, there are tinier objects, which are the quarks. They're bound together by the gluons. So what are the size of these quarks, antiquarks, and so on? They are even less than 10 to the power minus 19 meters. So it is this internal structure of the nucleons in terms of quarks and gluons that is the topic that we study in QCD or in hadron physics. So there are various interesting topics that are still not very clearly understood about the quark-gluon picture of the nucleons. One is, how do the quarks and gluons, which are collectively called partons, how do they stay inside the nucleon? How are they confined? What about their intrinsic motion inside the nucleons? They stay within the nucleon, they do not come out. So it is sort of many particles. So proton, neutron, they are spin half particles. So how is the spin half of the proton is made up from the spin and orbital angular momentum of these quarks and also gluons? That is also a question that has not been understood clearly. What is the spatial distribution of quarks and gluons inside the nucleon? Is it a uniform distribution? Is it not uniform? What happens if the proton or neutron are polarized? Okay, you can polarize a proton beam, for example, in a direction which is the same as the direction of motion or in a transverse direction. So how is this polarization affecting the internal structure of quarks and gluons or their interaction? Okay, all these are interesting questions that are being investigated now in hadron physics and in QCD. So in this talk, we'll discuss some of these interesting questions and how to study them. So how do we probe this internal structure of the nucleon? So nucleon structure is probed through high energy scattering processes. So you probe the nucleon, or let's say a proton, by an electron beam, let's say at very, very high energy. So this electron bombards with the proton breaks up. In the final state, you see many remnants, many hadrons. And this electron gets scattered. It's a high energy scattering process. So from these scattered products, one gets some idea of the structure of the proton, the internal quark-gluon structure of the proton. So this electron-proton scattering is called deep inelastic scattering, where the proton actually does not remain a proton after the scattering, it breaks up. So in the final state, one observes the scattered electron and nothing here. So all the remnants, we don't care what it has been produced. Okay. So actually this scattering of electron takes place through the exchange of a photon. So in the language of particle physics, this photon is called a virtual photon because this photon is actually massive. So real photons do not have mass, right? It is a massless particle. But we are not observing this photon. This is actually a mediator of this interaction at high energy. So this photon is actually massive, that is q squared, the 4 momentum square is not 0. And in order to study this process theoretically, one also defines a variable x, which is usually called the Bjorken x. Sometimes it is also denoted by xb. It is a ratio of these kinematical quantities, q square, capital Q square, which is also the virtuality, which is called the virtuality of this photon, and this twice p dot q. These are the 4 momentum of the proton, and this is the 4 momentum of this photon. And then there's another variable y. So the key point is that the cross section of this process, the differential cross section for this process, electron proton going to scattered electron and some remnant, can be written as sort of a product of two parts. One part is basically the scattering of the electron from a quark inside the proton. This quantity d sigma hat dq square can be calculated in perturbation theory order by order in the coupling. This is multiplied by another quantity, which let us say qx. This q of x is basically called the parton distribution or the collinear parton distribution. This is nothing but the probability to find a parton, that is a quark, inside the nucleon with a momentum fraction x. Okay, so this x is basically the longitudinal momentum fraction of the proton carried by the quark. So this part, parton distribution part, is a non-perturbative object. You cannot calculate parton distributions in perturbation theory order by order in the coupling constant. The advantage is that, the advantage of this framework, the fact that the cross section can be written as a product of a perturbative part and a non-perturbative part, is called factorization theorem. The good thing is
I have a small question. Why you say that it cannot be calculated perturbatively? So what is the reason behind that?
You cannot apply perturbation theory everywhere, right? So proton is a confined object. Quarks and gluons, quarks are confined inside. You cannot solve this system or this part of QCD using perturbation theory.
Maybe the answer is that the QCD coupling is order 1.
Yeah.
So there is no perturbation theory.
Perturbative parameter.
Doesn't work.
No. So Urjit, this part, the d sigma hat dq square, it can also be a QCD interaction. Okay. But this part can be calculated in perturbation theory.
Right.
Okay, that is what I'm saying. So the cross section has a perturbative part and a non-perturbative part. Out of that, this parton distribution, which is related to the probability.
I'm sorry, yeah, I take it back. But yeah, I think the idea of the gluons and how many they are and all that is very.
Yes, so this information that is contained in this part of the cross section is non-perturbative. So the basic point of factorization theorem or the predictability is that it separates the perturbative part of the cross section from the non-perturbative part. This perturbative part varies from process to process. Okay, there can be different processes. For example, there can be a final state that is different and all that. So this perturbative part, you have to calculate separately for each process. But the good point is that this non-perturbative part, q of x, is universal. Once you can extract it somehow for one process, you can apply it for any process. Because this is a property of the proton, not related
Asmita, there are two questions actually. So first is Ridish.
Yeah, so what do you mean by polarization of proton?
Yes, so proton beam can be polarized, right? Just like photon can be polarized, so proton beam can also be polarized. So you can define a polarization vector, right? So it can have a polarization.
Orientation of spin along momentum.
Yes.
I see. Oh, okay.
Projection of spin
Okay,
along
okay,
momentum.
Yeah, or perpendicular to the momentum.
okay, got it.
The next question is by Sumiran.
Yeah.
Hi, Asmita. So
Hi.
this factorization theorem that you said,
Mhm.
is there some other example in some other domain of physics where such a factorization happens? Do you know?
So in high energy scattering,
Mhm.
this is one example of scattering with electron and proton. There are other scattering like proton with proton and things like that. Right? Neutron with proton.
I see. I'm not talking in the context of QCD, sort of in
Okay.
general, in theoretical physics. Is there some kind of this kind of factorization somewhere else? Do you know?
Apart from high energy scattering process, I don't know where else it can be applied. This is a very, very remarkable thing in QCD because normally QCD is non-perturbative. QCD completely cannot be solved in perturbation theory, but still we can calculate cross sections, that is probability of interaction partly using perturbation theory because of the factorization theorem, because one part of the cross section we can calculate using perturbation theory and this part is separated from the non-perturbative part. That is the remarkable aspect of factorization theory.
Okay, okay, great.
But one has to remember that this factorization theorem is not valid for all high energy scattering processes.
I see.
Only in a selective few of them.
I see. I see. Okay.
And is there is there at the very beginning you can say that okay, these are the processes I can do this factorization and these are the processes I cannot do? Is
No,
there
factorization has to be proven.
Proven.
That
Okay.
certain cross section can be written in this way. People have done the calculation and they have proven factorization for some of the processes, even some more complicated processes. And then there is an order in the coupling, an order in perturbation theory up to which factorization holds. So
Okay.
you have to actually
Interesting.
actually show the factorization by doing calculation. It is not, you
Okay.
cannot just guess whether factorization theory is applicable or not.
Asmita, can I just make one comment?
Yeah.
Which might help people. It turns out that quarks will see weak interaction and strong interaction as well. But electron will only see weak interaction. And so the source of the factorization to an extent at least has to do with the fact that electron quark scattering can be calculated perturbatively because electroweak is perturbatively calculable.
Urjit, that is correct, but also
I agree that you have more complications. I'm just trying to simplify it for.
So that is a very good point. But instead of an electron, even if we have another proton here, so proton going to, for example, a pion.
Oh, yeah. No, but so long as there is virtual photon, right? Because it's only electromagnetic.
Yes, so there also you can exchange virtual photon as well as gluon. So there are all these probabilities that you have to take into account in order to calculate the cross sections.
Okay, thank you.
Actual factorization is not related to electron-proton or QED interaction. In QCD also, factorization works for some processes. Okay, so are there further questions?
No, not at this point of time. You can continue.
Okay, so I introduced the collinear parton distributions in the previous slide. That is the non-perturbative part, QX. Okay, so what are these collinear parton distributions? So here what happens is that electron and proton are moving at very high energy towards each other, let's say in some frame, and then they are scattering. So in this approach, what we are doing is that we are somehow assuming that the proton consisting of quarks and gluons, so these quarks and gluons are frozen in a plane transverse to the longitudinal direction. That is the direction in which the proton is moving. Okay, so all transverse, intrinsic transverse momentum of these quarks that is neglected in this picture. So the quarks and gluons, they have a momentum which is in the direction of the proton. Let us call P plus, that is called P. Let us assume this is the component of the momentum in the direction. And X is the fraction of this momentum carried by this particular quark. Okay. So these parton distributions then gives the momentum distribution of these quarks inside the proton. This X distribution of these quarks inside the proton. Apart from the momentum fraction X, these parton distributions also depend on the momentum scale in which you are probing the proton. So this momentum scale is basically nothing but the virtuality of this photon, capital Q square. That depends on the energy of your colliding particles. That is, overall energy momentum will have to be conserved, right? So Q square, the virtuality of the photon, is basically the scale, momentum or energy scale at which you are probing the proton. Okay. So these parton distributions apart from X depend on Q square. The advantage is that even though parton distributions are non-perturbative object, how do they change with the scale Q square can be calculated in perturbation theory. Okay. Next, let us come to another concept, which is the transverse momentum dependent parton distributions.
Sorry, Asmita, can you just define the patterns once more? I think I missed. I came slightly late.
Partons are quarks. Quarks are gluons that are inside the protons and neutrons.
Okay. Go on.
Okay. So they are collectively called partons, quarks, antiquarks, and gluons. Okay, next, the main topic of this talk are the transverse momentum dependent parton distributions, or TMDs. So collinear parton distributions assumes that in transverse plane, these quarks, antiquarks, and gluons are frozen. There is no transverse motion. Okay, only they are moving with the proton in the direction of motion of the proton. But actually that is not so. They are not really frozen. That was an approximation which works for the process that I discussed, electron-proton deep inelastic scattering. What happens is that sometimes in some experimental signatures, you see the effect of the intrinsic transverse motion of these quarks and gluons. What are these experimental signatures? For example, at Rick and Fermilab experiments from early 90s, people have seen very large 30% to 40% single transverse spin asymmetries. Now, what is single transverse spin asymmetries? Let us say you are colliding proton with a proton beam, two proton beams bombarding with each other. One of the two proton beams is polarized transversely to the beam direction. Okay. And then you measure the cross section for a production of a pion in the final state. You put some detectors and you are observing some pion. So these experimentalists found that the cross section for this production of pions depends on whether the proton spin or polarization is up or down with respect to the beam direction. Okay, this is hard to understand. It is polarized in the transverse direction, but the cross section for a given process depends on the direction of this polarization in the transverse plane. So single transverse spin asymmetry is defined as this ratio, d sigma up minus d sigma down by d sigma up plus d sigma down. That is the difference of these two cross section by the sum. At the denominator, it is just the unpolarized cross section. And this asymmetry turned out to be quite big, 30% or 40% that you see in this plot. So these kind of single transverse spin asymmetries cannot be explained in terms of these collinear PDFs. You can do some theoretical calculations. So for this process, people have shown that factorization is applicable, but you cannot explain these single transverse spin asymmetries. In order to explain it, you have to introduce the concept of transverse momentum dependent parton distributions, that is parton distributions which are dependent not only on x, the longitudinal momentum fraction of the partons, but also their intrinsic transverse momentum, k-pop or kt.
There is a question, Asmita, from Sumira.
Hi, so when you say polarization here, is it the relative polarization of the two beams, whether they are parallel or anti-parallel?
No, one beam is not polarized. One beam is unpolarized, that is, it has polarization in all directions, all probabilities. The other beam is particularly polarized by applying some magnetic field in a certain way.
I see. And what determines the up and down for in this way?
The direction of motion.
So it is polarized. I see. It is polarized in the direction of the motion or opposite to it?
No.
Transverse, right?
So let's say the proton is moving in the z direction, and in d sigma up, the proton is polarized in plus x direction. In d sigma down, the proton is polarized in minus x direction.
Okay.
This is called transverse polarization.
And the same would happen for, but what decides plus x, which direction is, whether left is plus x or right is plus x?
Yeah, so that you have to define, you have to put a detector or so on, but whatever it is, in one case it is polarized in a certain direction relative to the beam, and in the other case it is polarized in the opposite direction. In the transverse plane.
Okay.
That you can do, right?
Yes.
The magnetic field.
I see. Oh, very interesting. Okay, thanks.
There is another question from Sai.
Yeah.
So Asmita, like so from standard scattering theory, I just want to kind of just set myself up essentially for the conversation. So in standard scattering theory, for instance, I think this is like a selection rule that prevents you from seeing any scattering in the perpendicular direction, right? So are there such scattering, like how should I think about scattering of you know, of these particles? Like this is a scattering experiment, right?
No, but it is not scattering in perpendicular direction, right? I am saying that the beam is polarized in the perpendicular direction, right? Orientation of the spin. So it is getting, so these two beams, one is polarized, one is not polarized. They are bombarding with each other.
Sorry, I missed it because of the, and I got confused because of the diagram. So, so sorry, I'll let you speak.
Okay, yeah, so in the final state, after the scattering, there are no protons, okay? So there are many particles scattered in all possible directions. We don't care, but we have placed a certain detector which have the ability to detect one pion, which is another particle. Okay, we are observing this pion in the final state, and this xf is some kinematical variable related to the longitudinal momentum fraction of that pion, and this gives an for that process. Okay, an is defined here. Okay.
Is space on this diagram at all? So I think the because I don't understand what XF is, I'm getting a bit
XF is not position. XF is basically related to the longitudinal momentum of the final state pion. It is basically P longitudinal twice P longitudinal by square root of S. That is, it is the longitudinal momentum of the final pion with respect to the total energy of the initial state.
Okay. So this is something, okay.
Yeah. It is called Feynman variable. Yeah, any other question?
Not immediately, I think.
Okay. So these TMDs, transverse momentum dependent parton distributions, play a role not in all processes, but in some processes where the transverse momentum effects are observed. For example, in the previous slide, I talked about a pion production in the final state, right? This pion is observed with a certain transverse momentum with respect to the beam direction. So in this kind of processes, these TMDs play an important role. So for this kind of process, for example, instead of proton-proton scattering, let us still consider electron-proton scattering. And in the final state, I am observing some hadron, for example, pion. Okay. So the differential cross-section for this kind of process, this is also called semi-inclusive tip elastic process. This can again be written in a factorized way in this way. So this FQ is the TMD PDFs, transverse momentum dependent parton distribution, similar to the parton distribution that I introduced earlier, but it depends on K-pop also. This D sigma hat is the hard scattering cross section. This part is calculable perturbatively. And there is another function DHQ, which is called fragmentation function. This basically is related to the probability that a quark in the final state becomes a hadron like a pion. You don't observe quarks or gluons in nature. What you observe are hadrons like protons or pions or something. So these quarks and gluons produced in this perturbative hard scattering, they combine with each other and they become hadrons. So this information is given in the fragmentation functions. Like parton distributions, fragmentation functions are also non-perturbative object. It is this hard scattering for each process that can be calculated in perturbation theory. Okay, so this is basically a generalization of the factorization that I shown in the first slide. This is a generalization because it also incorporates the intrinsic transverse momentum K-pop. As I mentioned before, this kind of factorization is not proven for all processes. There is another problem here. The parton distributions, the predictability of the factorization theorem was that the collinear parton distributions was independent of the process. These are non-perturbative objects. But once you find it for one process, you can apply it for the prediction of cross-section for another process. That is not so for TMD parton distributions. These TMD parton distributions depend on something which is called a gauge link or Wilson line that makes it dependent on the process. Okay, we are going to look into more of this. There's another thing like collinear PDFs. These also depend on the momentum scale Q square. But how it depends on the momentum scale is different from the dependence of collinear PDFs. Okay, next I come to the particular topic that I want to talk about. This is Sivers asymmetry in semi-inclusive deep elastic scattering. So semi-inclusive deep elastic scattering is the process that I just talked about. Electron-proton scattering. Proton is polarized transversely. In the final state, you are observing the scattered lepton, L prime, lepton means electron, plus some hadron, for example, pion with some transverse momentum. Okay. So the cross section of this kind of process, differential in various kinematical variables, in general looks like this. So what are the meaning? You see some angles, phi's. So what are these angles? These angles are various azimuthal angles. So basically, if you look at this diagram, this is the initial lepton, this is the final scattered lepton. So these two leptons form a plane which is usually called the lepton plane. Then the final hadron, which is observed pion, for example, has some transverse momentum with respect to this plane. Okay, so phi h is the azimuthal angle between these two planes. On top of that, the proton is polarized in a transverse direction. Okay, so S is the polarization vector. So phi s is the azimuthal angle of this polarization vector with respect to this plane as shown here. So these are the azimuthal angles, and the cross section depends on these azimuthal angles, and there are different terms which depend on different cos or sine or something of these azimuthal angles. And these are the coefficients that are functions of the TMDs. For example, you see this term sine phi h minus phi s. The coefficient of this particular term depend on a particular TMD which is known as Sivers function. So coefficient of different azimuthal modulations are functions of different TMDs. Now a little bit more about the TMDs. There are different kinds of TMDs, or transverse momentum dependent parton distributions. At leading order, if we want to look into a quark inside the proton, there are 8 TMDs. So each of these TMD give different kind of information about the quark inside the proton. Okay. For example, this TMD F1Q is the probability to find an unpolarized quark with longitudinal momentum fraction x and transverse momentum k-pop square inside an unpolarized proton. Okay. So this function, Sivers function, is the probability to find an unpolarized quark with momentum fraction x and k-pop square inside a transversely polarized proton. Okay. So out of these 8 TMDs, only 3 TMDs survive if you do not care about the transverse momentum. In other words, if you integrate over all transverse momentum of the quarks. Okay, these are the 3 in blue. 2 of these TMDs are odd under time reversal transformation, Sivers function, and this is called Bohr-Mulder's function. And these 3 are even under time reversal transformation, but they also vanish under transverse momentum integration. Out of these 2, this talk I will mostly concentrate on the Sivers function. So as I said, each of these TMDs are very, very interesting because each of these give different information of the quark-gluon structure and some correlations of quarks and gluons inside the nucleus. And each of these TMDs appear in different azimuthal modulation, right? As I showed, Sivers function appears in the sine phi h minus phi s, then some other TMD would appear here. So that means if we can extract this sine phi h minus phi s part of this cross section, then we can extract the Sivers function. Okay. Similarly, these azimuthal modulations are the way to extract different TMDs. Now, what is Sivers function? So Sivers function, as introduced by Dennis Sivers in 1990, gives the probability to find an unpolarized quark inside a transversely polarized nucleon. It basically gives the correlation between the quark intrinsic transverse momentum, K-pop, and the transverse spin of the proton. Okay. So this is a non-perturbative object. You cannot calculate Sivers function as well as other TMDs in perturbation theory. In some models, however, it is related to the orbital angular momentum of the quarks. This is also a highly interesting topic these days in hadron physics. The Sivers function, if you apply time reversal transformation, so I haven't shown it, but Sivers function has an operator structure. If you apply time reversal transformation to this function, it becomes odd. So it changes sign under time reversal transformation. So physical effects are not time reversal odd. Okay, so there's time reversal symmetry there. So Sivers function has to combine with another time reversal odd effect to give an observable asymmetry. The Sivers function, like some other TMDs also, the operator structure, as I'm going to show below, contains a part which is called gauge link, okay, in order to make it color gauge invariant. So we are doing QCT, quarks and gluons inside the nucleon, they interact through a particular interaction process or a theory, which is called quantum chromodynamics or QCT. So like quantum electrodynamics, this is also a gauge theory. Okay, there is a gauge symmetry. So this is a gauge theory. And the observables in terms of quarks and gluons, whatever observables we have or whatever quantity we observe must be invariant under color gauge transformation. Okay, so these TMDs has a certain operator structure. There should be a particular thing there which is called gauge link or Wilson line, which ensures this gauge invariance. Okay, this is from a theoretical point of view. I'm going to explain what it means physically. So this gauge link is also present in collinear PDF, but there it actually is process independent. So the structure, operator structure of these TMDs is actually something like this. So this is a quark field, this is another quark field. So in between there should be some gamma matrices sandwiched. Okay. So in TMDs, even if one chooses a particular gauge, the effect of gauge link remains and in fact plays an important role. So this statement is slightly technical. Let me skip this sentence. But what I am saying is that this gauge link or Wilson line, which gives the process dependence to the TMDs, are very important for time reversal or TMDs like Sivers function. It can be shown that unless you take into account the effect of this gauge link part carefully, Sivers function would become zero. And in fact, it is actually not zero because people have observed the corresponding asymmetry experimentally. Physically, what is this gauge link? Okay. So this gauge link is basically exchange of soft gluons between the perturbative part of a process and the non-perturbative part. So as I said, for some processes, there is this factorization, that is, you can separate the transverse momentum dependent distribution part from the perturbatively calculable hard part. Okay. Consider a particular process, that is this semi-inclusive deep elastic scattering, as I was just saying. This blob, okay, so on the left hand side of the plot, or there is a dashed line in the middle, this is basically the final state. This left hand side, this is the incoming proton, and this gamma star is the virtual photon that is basically coming from that electron. Okay, so this gamma star does not interact with the proton directly, so a quark comes out from the proton, and then this gamma star, the virtual photon, interacts with the quark. This quark goes and makes some hadron or something here. And this is the amplitude star. So amplitude star makes the cross section. So this is the same thing. So this blob is basically the non-perturbative TMD part that I was just discussing. So the TMD is sitting inside this blob, and this is the hard interaction. So this gluon line is basically exchanged between this quark line and this blob. So this blob basically means many quarks and gluons. Okay. So this is called a final state interaction because the interaction of gamma star and quarks happens left hand side of this gluon exchange. Time is flowing from left to right here in this part. So in semi-inclusive dim elastic scattering, there is a final state interaction. You cannot rule out the possibility of this. This is only one gluon that I have shown in this picture. There can be many gluon exchanges between the soft part and the hard part, that is non-perturbative part and the perturbative part. Okay. But in some other processes, this gluon may originate from before the interaction with gamma star. This is another process, Drellian, which is a PP collision, proton-proton collision. In the final state, you observe electron-positron. So in that case, actually, it can be shown that this quark, before interacting with another anti-quark from this blob, it can emit a gluon, and which can get absorbed in this soft part. So this is a different kind of gluon exchange. In theory, we call this kind of gluon exchange initial state interaction, and this kind of gluon exchange final state interaction. Okay. So actually, functions like Sivers function will depend on what kind of interaction it is, what kind of gluon exchange is there for your process, whether it is an initial state interaction and whether it is a final state interaction. Because actually this gluon is contributing to the blob. You see, this is connecting to the blob because it is contributing to the blob, and Sivers function is sitting inside this blob here. Okay. In fact, people have found that Sivers function in Drelian process, that is this kind of process, is same in magnitude but opposite in sign compared to the Sivers function probed in this process. However, more complex processes have more complex gauge link structure, and factorization is not always guaranteed. Any questions up to here?
No, we don't have any.
Two people ran away.
Can I,
Urjit, yeah.
Can I try to rephrase what
Yeah.
you were saying? I'm trying to understand it. So this thing that we needed a link between psi at y and psi at 0 means that the separation is somewhat quote large, and so it is a low momentum limit. So is it an effect that is going to be seen in the low momentum end of the Parton distribution functions?
No, Urjit, it is present always. So the distance between the two quark fields, okay, it is not really depend on the magnitude of the distance. This operator structure, psi y minus and psi 0, you really do not see y minus. Eventually in the observable, you integrate over y minus. Because the quark that you are probing can be anywhere inside the proton.
Right.
Okay. But whatever it is, there will be this gamma is not the gauge link anyway, but there will be a gauge link that is sitting here. This Wilson line will depend on the direction of the separation, whether it is along the light cone direction or whether there is a perpendicular component of it or not. Not really the amount of separation.
Okay.
Rather,
I just thought that maybe the line is required, a gauge invariant line is required because they actually are very low momentum objects. And
no, it does not depend on low momentum. No. Because you are not seeing the momentum corresponding to this separation is not relevant here because you have to integrate over this separation. Okay, so any other question?
No, there is not much. So maybe we can finish in 10 minutes so that we have some.
I haven't even started.
Oh, don't worry. We have 15 minutes.
Okay. So gluon Sivers function is the Sivers function not for quarks but for gluons. So as I said, inside the proton there are not only quarks and antiquarks, but these quarks and antiquarks are bound with the gluon. So you can also have a gluon taking part in your interaction. Okay, that is also possible. So in that case, your Parton distribution will be related to the probability of finding a gluon inside the proton. That also may be important for your process. So Sivers function for the gluons can again similarly be defined. But the problem is that very little is known so far about the gluon Sivers function. And because of various reasons, people in this field are nowadays very interested in gluon Sivers function. One of them being the fact that some people have shown that it is related to the orbital angular momentum of gluons, okay, which is again so far very little is known about it. And then there is this gauge link and process dependence of this gluon Sivers function. That also people want to see experimentally. Now process dependence of the gluon Sivers function, because it involves the gauge fields, are actually more complex. However, it can be shown by these people, where I was also a contributor. Gluon Sivers function for any process can be written in terms of two independent gluon Sivers function, one containing a charge conjugation even operator, which is usually called F type, and the other called D type. So there are some constraints from phenomenology on gluon Sivers function. However, they are not applicable always. And as is known, Jepschi production, which is a heavy quarkonium particle, C bar bound state. Jepschi production is an effective way to probe the gluon Sivers function because gluons are probed. Okay, so Jepschi can be produced in gluon virtual photon collision, for example, at leading order. So Jepschi production process at electron-proton collider would be an effective way to probe the gluon Sivers function. So here I mean talking of the electron-ion collider, that is a planned future collider at Brookhaven National Lab. So we here in our group in IIT Bombay, me and my students and postdocs since several years have been theoretically calculating the asymmetries and cross-section for the production of this Jebshai in the kinematics of this future electron-ion collider. Okay, so I won't be going to the details of this cross-section. Do you want me to go into the details of this calculation? No.
Yes.
Maybe
That was already a no.
why is JSI the more relevant system in which to look for this?
Yes, because I am going to show the sub-process.
Okay.
The sub-process that produces Jebshai at leading order is a gluon-initiated sub-process. So there is large contribution coming from gluons.
So sorry, I have a question, silly question.
Yeah.
So what is this Jebshai that you're saying? Is it a particle?
Yeah, Jebshai is a particle. It is a bound state of a charm quark and an anti-charm quark.
Oh, I see.
Charm is a kind of heavy quark. Okay. So Jebshai, it is called a meson. It is a bound state of a charm and anti-charm, C-bar system.
I see. Okay.
Can I interject a little bit? People may be puzzled. The point is this CC bar was almost simultaneously discovered by two different groups. And one of them called it J and the other called it Psi.
Yeah.
And so later they converged on calling it J/Psi.
Oh, goodness. Okay.
Yes. So this is the process that we are looking into. Electron colliding with a transversely polarized proton. In the final state, you are observing a Jebshai and the scattered electron. So as we said, here also the factorization is applicable. Cross section can be written as a product of these terms. So L nu prime depends on the lepton only. Phi G part depends on the Sivers function and other TMDs. And this M mu nu star depends on the gamma star G going to Jebshai process. Oops. Let us skip this part. Okay. So this is the leading order process that contributes here. Okay. So here electron-proton interacts and produces a Jebshai. So the corresponding perturbative process at leading order is given here. So a virtual photon comes from the electron and from the proton you get a gluon. So these gamma star and gluons interact like this. So this is a quark line. So this is a C and C bar. This is a heavy quark. And these C and C bar, they combine with each other and produce this Jebshai particle. Okay. So this gamma star and gluon interaction and the production of C bar is a hard process which can be calculated in perturbation theory. However, how this C bar, okay, produced in this hard process forms a Jebshai, that is a non-perturbative process. Okay. So there again one cannot apply perturbation theory. So there are various models in the market, theoretical models that deals with the production of this non-perturbative Jebshai production from C bar state. So in this calculation, we have used the most popular of this production mechanism or model. It may be called a production mechanism, which is based on something called non-relativistic QCD and color octet model. So the idea of this model for Jebshai production is that these quarks are heavy, right? So they have a relative momentum in this hard process, that is K prime, and K prime is quite small. So you can expand this amplitude in a Taylor series expansion and keep only the first term and the second term.
Asmita, one question.
Yeah.
Yeah. Ridesh.
Yeah.
Yeah, Asmita, I have another question. So the way you're presenting, it seems like the entire process has two non-perturbative parts.
Yes.
And one perturbative scattering
Yes.
section. Right. So the scattering, the perturbative part, I understand you follow the standard prescription to calculate the cross section. How are the non-perturbative parts calculated? Like the one you said you get it from, there are many available in the market. What does that statement mean?
So there are, so the how, okay, now I am talking of the non-perturbative part related to the final state, okay?
Right.
Non-perturbative part for the initial state is the Sivers function here that we don't really understand clearly, and what we are going to calculate, if it is measured experimentally, we will give you some idea on it, okay? But the non-perturbative part in the final state, there are several ways to calculate it, okay? So one is a lattice calculation. Then there is another way, that is again by fitting experimental data. You get some results from experiment, you fit in the perturbative part of those processes. For example, some unpolarized scattering where the parton distributions is more or less known. Then from there, you can extract this non-perturbative part associated with the Jebshai production.
I see. So is it fair to say then the non-perturbative part, either you can fit it from experiment phenomenologically and then do your perturbation part analytically, or?
It's not that simple. Okay.
Oh.
So some of the complications associated with the final state is that you see this quark-anti-quark pair, heavy quark C-Sivers pair can be produced in the hard process in various quantum numbers. Okay. Different color and angular momentum quantum numbers. They can be color singlet, they can be color octet. Quarks and gluons carry colors, okay, like red, green, and blue. These colors have nothing to do with your everyday perception of colors red, green, and blue.
Sure,
So
sure.
these colors are the quantum numbers associated with the QCD gauge group. Okay, so quarks and gluons, they are colored, but in reality, you cannot observe any colored particle. Everything that you observe is colorless. So Jebshai is colorless. But nothing stops this quark-anti-quark pair to be produced in a color state. So somehow this quark-anti-quark pair can be produced in a colored state. They can also be produced in a colorless state. You have no idea what are their quantum numbers because you are not observing them. Okay. So you have to consider all the probabilities of different kind of color, spin, and angular momentum quantum number pairs created here to form your Jebshai particle whose quantum numbers you know very well. Okay, so that is done in a systematic way by expanding this amplitude in terms of the small velocity parameter. This is the idea of non-relativistic QCD. Basically, you are using the fact that the mass of this heavy quarkonium is much larger compared to this velocity parameter. And different coefficients of these different terms, which are called LDMEs, long distance matrix elements, these are actually obtained by fitting experimental data. Okay, so let me show you some of these results. Like for example, this amplitude is written as a product of these terms, where for example, this part psi gives the eigenfunction of some orbital angular momentum L. Okay, this is the corresponding Klebs-Gordon coefficient. This is the perturbative part that comes from the Feynman diagram. And this is again the spin projection operator. So this can be a spin triplet, this can be a spin singlet. So all these things will have to be taken into account. Basically here the theoretical estimates are arranged. Theoretical estimates for this amplitude are arranged in double expansion. One is in terms of V, which is non-relativistic, and then again the coupling. And the final result will involve contribution from different states. So these matrix elements with different operators basically indicate from which state this C-Sivers, this quark-anti-quark pair is evolving to become a Jebshai. It can be a 1s0 state, it can be a 3p0 state, it can be a 3p1 state, 3p2 state. These are the states that are allowed here. Okay. And this is the amplitude, or this is actually the contribution to Sivers asymmetry that we have calculated by feeding in all those informations in NRQCD based color octet. And these are the LDMEs, these matrix elements, these cannot be calculated in perturbation theory. These matrix elements are either calculated on lattice or one can fit them by using experimental data.
So also one question, when you say calculate on a lattice, what exactly is done? Like Monte Carlo, or like what kind of?
That I am not sure. There are lattice data. I guess your friend Shayantan would know. But there is some way of calculating these quantities on a lattice.
But numerically.
Can I just, I mean, I don't know at what level this question is, but the point is QCD has another way of dealing with it in the non-perturbative limit, which is to put it on a lattice. You do a gauge theory on a lattice, and that data is what is being spoken.
But Urjit, does it mean that basically summing over all trajectories?
No.
Yeah, I don't think
discretize. You discretize your continuous space-time.
Yes, but then what, I mean, what does the numerical calculation mean there? Summing over
exactly, that is also
trajectories, isn't it? Quantum trajectories using this path integral thing.
Yeah, probably.
Yes. The lattice is a way of calculating the functional integral of QCD for the long wavelength.
But under heavy approximation.
Yeah.
Okay, got it. Yeah.
The main, yeah.
Ra-
So
Rama wanted to say something actually.
Yeah, I said the lattice gauge theory people use placket formalism and this heavy duty computation using clusters and all.
but yeah, it is a way of doing functional integral in
Yes.
for gauge variables.
Okay. Okay, so this is the work that was done by my previous student Sangam Rajesh and published here. And we have used some of these extractions of these LDMEs in the predictions. So in that work, we also taken into account the evolution or the scale evolution of the Sivers function. There are various ways to take into account that. And these are the numerical estimates that we gave for the electron-ion collider for the Sivers asymmetry for this particular process. So we have used different models of the Sivers function and we obtained negative asymmetry. And we found that the asymmetry depends on the model parameters for Sivers function that we use. We also, there are some data from a particular collaboration in CERN, which is called COMPASS. They also have some data. There are actually basically 2 data points with huge error bars. We also compared with those data. And overall, there is agreement, although because of the huge error bar, it's hard to really compare, but one of these models results is actually lying within the error bar. So that is all we can say here. But more data are definitely needed on these variables. So another process that can shed light on this topic is inclusive photoproduction of Jepchai. So here basically we say that the photon that interacts with the gluon to produce Jepchai is almost real, it is not virtual. And there is a way to extract this data. So this can also be used to obtain information on the gluon Sivers function. So we did the calculation here of the single spin asymmetry. It is more complicated, by the way, because here the number of Feynman diagrams that we calculate, that we contribute is 8. So we calculated all these amplitudes in the framework of NRQCD based color octet model. So my present student Raj Kishore was also involved in this calculation. And we gave predictions for electron-ion collider. So this is an example, for example, one of the amplitude square for the 3p1 state octet. This looks like this. So there are several such contributions. Most of them, this was, I think, the smallest contribution. And then this is how the asymmetry looks like. So different curves here actually are estimates using different models for gluon Sivers function. So the results again are very much dependent on models. Some of the models in fact give positive asymmetry and some of them give negative asymmetry. So these are a few calculations that I briefly show here. These are the first calculations in the literature of these processes using NRQCD based color octet model. There's no other calculation of these exist in this literature. And all these calculations done explicitly by Rajesh and Raj will play a vital role in the data analysis in the future from this electron-ion collider. So we also compared with some old data from HERA for unpolarized process, okay? So we basically compared the cross section. So these are the experimental results. And this red dashed line is when we include the possibility that the heavy quark pair is produced in color singlet as well as color octet state, whereas this black dash curve is when we consider only contribution from color singlet state. And you see from these results is that both color singlet and color octet contributions are important to explain the HERA data. Okay, this is another comparison.
Asmita,
yeah,
maybe we can try to
yeah, that's what
finish
I'm
in 5.
So let us keep
Yeah.
the last
Thanks.
topic, which is again another process, back-to-back production of Jepchai and Jet. And this is again finished in this year. And these are the predictions for the asymmetries for electron-ion collider and some more numerical results. And that brings me to my conclusion. So basically in this talk, we have shown that the single spin asymmetry in Jepchai production in electron-proton collision provides a direct way to access the gluon Sivers function. And we obtain sizable Sivers asymmetry. We have given the estimates of this asymmetry in NRQCD based color octet model. We have compared with COMPASS result. We have compared our calculation for unpolarized process from HERA result. And yeah, so this is it. Thank you.
Thank you. Thank you very much for this nice talk. So is there questions?
I have a question.
Yeah.
Yes, Trisha.
Yeah, sorry.
Trisha, I can't see Trisha.
Yeah, so some basic clarification.
Yeah.
So this all these diagrammatics, etc. They are all about the perturbative things which you do via Feynman diagrams, right?
Yeah.
Now the hard part, and one of the hard parts, the non-perturbative thing. For those, since no analytic method is really meaning it's kind of, you have to make some model. Sivers is one of the examples, right?
Yes, yes.
Yeah, so that means in all these calculation, this non-perturbative part, you cannot do an exact calculation, but you can do still a numerical calculation, right? Which will be somewhat approximate, which can, without going through all the Sivers thing, basically sum over all possible quantum numbers, color, charm, momentum.
No. I think there is a confusion. Sivers thing was for the initial part. Okay. Sivers effect is at the initial part of the scattering.
Okay.
So that is related to the gluon that is coming from the proton.
Okay.
Okay. And this non-relativistic QCD part, that is for the final state. That is when this quark anti-quark becomes a Jepside. These two are separate things associated with the same process.
But if Anirban is asking, if Anirban is asking if there is ab initio method for QCD, there is none.
Yes.
Yeah, so there are
the
some
only
ab
way
initio
of doing it.
calculations. There are some ab initio calculations for some of these parton distributions. Some groups do it. Okay, some groups also do lattice calculations. But the most popular method of extracting information on these parton distributions, that is non-perturbative object, is by doing an analysis of experimental data. Okay, like this unpolarized parton distribution, unpolarized collinear parton distributions, right? By now are quite well known because people have lots of data from lots of experiments around the world. Okay, as soon as you can somehow fit those data by doing a global analysis at a particular momentum scale, you are done, because then you know the evolution equations, because you can evolve it to another momentum scale associated with another experiment using this QCD evolution equation.
So that is the model building part, phenomenological model.
It is the phenomenology part, but they do it in a very, very sophisticated manner these days.
Yeah. So okay, one more question here. See, as I understand, in many body, quantum many body, the number of players, there the complications are due to correlations mainly. But but here in this particle context, there are three quantum numbers. There are number of players are very small actually. One proton.
That's the main problem. Number of quarks and gluons inside a proton is not constant. Number of quarks, antiquarks, and gluons inside the proton changes with your probing scale Q squared. That is the main problem of QCD here.
Okay. So essentially,
the more energy you are putting in probing, the more number of quarks, antiquarks, gluons you will be seeing. It is not constant.
Okay. So in your calculation, you sum over all such processes, meaning all such possibilities that the number can fluctuate.
So in our calculation, we have to sum over all such processes, meaning that in our observable, we have to integrate over X and A up.
Yeah, that's what I mean. Yeah. Okay.
So before Sumiran,
NRQCD octet approach, the octet is just some color octet is just some approximation. No, are there actually virtual states like that, or?
No. So the idea of NRQCD color octet is that this C bar is produced in color octet state in the hard interaction. Then it may emit some soft gluon to become a color singlet Jepside.
Oh, I see. Okay. NRQCD is non-relativistic.
Yeah, so
because they are very heavy. Yeah. I'm just telling for audience.
Yeah. So you are assuming this K prime is very small, so there's a non-relativistic velocity parameter. You are expanding your process or amplitude in terms of that.
That is why I come to my point that ultimately these things must be contributing at longer distance and low momentum. Only then also angular momentum will contribute, because angular momentum.
Non-perturbative means it is slightly lower momentum, right? It is non-perturbative physics.
Exactly.
So these are soft gluons, means lower momentum gluons. But eventually, all these perturbative and non-perturbative parts, they are part of the same process. You are observing something, like you are bombarding electron-proton. In the final state, you are observing a Jepsai. Your observable, what you are seeing here, contains contribution from both the perturbative part as well as the non-perturbative part.
Asmita, there is a question from Sumiran.
Yeah.
Yeah, so of course these calculations are too technically advanced for me to follow fully. But is it possible to put it in words? What is the mechanism behind the spin asymmetry observations?
Yes, so the mechanism I actually explained here. Basically, what is happening is that you have, for example, a proton, right, which is polarized in a direction transverse to the direction in which it is moving. Okay. Then what is happening is that there is a quark inside this proton. Let's talk about quark to simplify the matter. There is a quark inside this proton. This quark is unpolarized. Okay. This quark has no preferred spin orientation.
Okay.
And it has some particular transverse momentum kappa.
Okay.
Okay. Then actually this probability of finding this particular quark with momentum fraction x and transverse momentum kappa somehow depends on this proton polarization S.
I see. So because there is some entanglement.
There is some correlation between all these.
Correlation between.
Yeah. And this Sivers function gives you that correlation.
So the game is to sort of come up with a functional form for that observed correlation.
Yes, or get an idea of how big that correlation is. You cannot measure this particular Sivers function, right? You are not measuring Sivers function. All you measure is the probability of producing a Jepsai. You are bombarding electron-proton and you are seeing a Jepsai. Somehow an observable associated with that Jepsai production gives you information on this correlation.
See.
That particular observable is a particular azimuthal modulation. That is, if somehow you can extract a part of this production cross section that depends on this sine phi h minus phi s, that will give you directly an idea of this particular correlation or the Sivers function.
I see. So sort of a spin up incident particle might interact in a different way.
Yes, spin up means transversely.
Yeah. Transversely spin up will sort of correlate with the quarks, etc., inside the proton in a different way than the spin down for some reason.
So going with
spin up is the proton and the quark is inside the proton.
So going with Sumiran's question, is it like an effective spin orbit interaction inside your nucleus?
Yeah, in some models, it is hard to say because you have to assume a model for this quark structure of the proton in that way, okay, in order to calculate that. And that is, people actually have done that. So in some model, it is related to the orbital angular momentum of the proton, but it is a model dependent state.
You mean how the incident spin couples with the momentum of the quark to its angular momentum, because that creates an effective moment.
But you have to assume a model in order to calculate that.
Yeah, got that part. Yeah, makes sense.
So, but in QED and in other, there is no such spin asymmetries in nature, is it?
QED, the electron is a fundamental particle, right? So electron, there is a spin orbit coupling of the electron, of course, but that is different.
I see.
Here you have an extended object, some internal particles. These particles also have motion.
Right. I see.
Okay, and this S corresponds to the extended object's spin polarization.
So somehow I can imagine, it's what Hirdish is saying. The spin is coming, it sort of magnetizes the proton.
Yeah.
And then that changes the interaction. So like say scattering from a magnet for a constant.
Yeah, that's right. The effect of polarization of the extended object or the proton somehow affects the quarks and gluons inside.
I see. Okay, thanks.
So is there other questions?
Is there any difference between treating up quarks and down quarks in the proton?
Yes, you have to take into account. So I have put a Q by P here. So Q basically is the flavor of the quark.
I see.
So of course you don't know which flavor of the quark is giving you your Jepside. So you have to sum over all possibilities, all flavors, quarks, antiquarks, and gluons. Sivers function for up quark is different from Sivers function from down.
Okay, so it seems that there is no more urgent questions. So let me thank Professor Mukherjee for this nice overview talk. It was very inspiring.
Right.
So thank you very much. And I also thank everyone in the participant to participate in our virtual faculty seminar. Thank you.